Hey, ladies and gentlemen, welcome once again to the Simkins Physics Corner. It's your host, Mr. Simkins, with AP Physics, Simple Harmonic Motion. Let's get into it. Stuff that goes back and forth. Our first example, we have a block on a horizontal surface attached to a horizontal spring oscillator. The spring is going to have a K of 50 Newton meters. The other end of the spring is attached to a wall, and there's negligible friction between the block and the horizontal surface. Sweet. When the spring is unstretched, the block is located at our equilibrium position. The block is then pulled 2.3 meters, released from rest, so that the block spring system oscillates between those two places. What is the magnitude of the acceleration of the block and the direction of the net force exerted on the block when it is located here? So what is it asking us about? The magnitude of the acceleration. Let's talk about what things are contributing to the acceleration over here at 0.3 meters. Well, the first thing we want to consider is that block here, what forces are acting on it. Well, at that point, the biggest force, and really the only force that we have to worry about in the horizontal direction anyway, is the force of the spring, which is negative kx. So we do know the k and we do know the x, therefore we know how much force is acting. Now, the question asked about magnitude of acceleration. Mr. Simkins, why are you considering force? Well, because of Newton's second law, of course. Sigma F equals ma. So let's go ahead and do that. The net force there is the force of the spring, and it's going to cause the mass to accelerate backwards at some rate. So I'm going to go ahead and expand this work to down here, and we say that kx is equal to ma. Now I will say negative kx. I'll say right is positive, left is negative. And if I do that, I have 50 newtons per meter. I have 0.3 meters. I have a mass of 0.5 kilograms. And all I have to do is algebra good to get an answer for the acceleration there. So 50 times 0.3. Then divide by 0.5 for our mass is going to get us an acceleration of negative 30 meters per second squared. When it says what is the magnitude of acceleration of the block, 30 meters per second squared, and the direction of the net force exerted on the block, we would say the force is to the left. Right? As you oscillate back and forth, when you reach this point, you're slowing down, stop, come to rest, you're about to turn around and go back. So some people would have an issue, say, Mr. Simkins, how can you be at rest and accelerate to the left? And I would say, well, acceleration isn't velocity, right? What does that mean? It means we were moving to the right with velocity, and the acceleration was to the left, slowing us down. Then we were at rest, and the acceleration to the left was turning us around, and then we come back, our velocity is now to the left, and our acceleration to the left is speeding up. So as soon as we pass that equilibrium position and we're on the right side in this picture, the net force is always to the left, meaning the acceleration is always to the left. Keep trucking. We have a cart of 2 kilograms is on a horizontal surface attached to a horizontal spring. Then we're going to put a block on it. I better start drawing this probably. So a cart is on a horizontal surface like this, and we got a little cart guy, and he's got a mass on him. I'm on the wrong problem. Try that again. Cart mass guy, here he is. This is 2 and this is 1. The other end of the spring is attached to a wall and there's negligible friction. Now this should be a horizontal surface. I just got a little sloppy there. The cart block spring system then experiences simple harmonic motion as described in the graph that shows the velocity of the cart as a function of time. The maximum spring potential energy is most nearly what? Well, I'm training all of you guys, my physics students, whether you're here or halfway across the world, to think about 3 questions when you see a graph. What is it a graph of? Does the slope mean anything? Does the bounded area mean anything? Now in this case, probably neither of those things matter, but let's see what we have. The maximum spring potential energy. So that's saying what's the biggest US we can get? The spring potential energy is derived as 1/2 kx squared. Interesting. So we don't know anything about x, but we do know something about the velocity. Let's see what strategies we can leverage with those 3 graph questions to try to chip away at this one. Now, simple harmonic motion is really about energy, right? As the oscillator comes all the way to this position over here, it is at rest, so it has no kinetic energy, but it has all spring potential stored energy. And as it whips through the middle, through the equilibrium position where there is no force acting on the spring, right around here, that is going to be all kinetic energy. So what can we say about the amount of spring potential at rest and the amount of kinetic when there's no spring? We can say that they're equal to each other. So we're going to set that equal to big K, not to be confused with little k, the spring constant, big K being the kinetic energy. Okay, so this is getting to be a long 4-part equation. Let's make this a little bit easier here. we have it like this. We have 1/2 mv squared. We're going to cancel both halves, algebra, and it's asking us for the maximum spring potential energy. So we're kind of making our way there. In fact, maybe a better strategy, since it's asking me about energy, maybe I should just stick to energy. Let's go ahead and try this out. 1/2, the mass is going to be 3. That's because there's a 2 kilogram cart with a 1 kilogram block on top of it for a total of 3. Now, V, you're saying, where are we going to get that from? Think about what this graph is showing. It's a graph of velocity, right? It says that our maximum velocity is 0.8 meters per second. And what that means is as we whip back and forth, like through here, if our velocity is 0, think about it for a second. Where is that? Oh, that's at one of the sides, right? So when we have positive velocity, that's like over here, we're moving to the right. That would be like right at the top of the graph. When we have, that would be moving through the middle as we move to the right with maximum velocity. Where would our velocity reach 0? When we're all the way at the edge. And then we turn around, that's why we go to negative regions, and so on. So with our kinetic energy, we just do a little bit of algebra here. I'm going to go ahead and make sure we're being careful with our calculator. And our maximum kinetic energy that we're going to have is 0.96 joules. Mr. Simkins, did you get lost? It said, what's the maximum spring potential energy? Oh, if the total kinetic energy, when it's all kinetic through the middle, is 0.96, then what's the total maximum spring potential energy all the way at the edge when it's all spring potential? The same number. Sorry, that should be a joule there. So that's 0.96 joules for our spring potential energy. Let's move on to the next question. We saw that energy works for simple harmonic motion. Here we have a block to a horizontal spring. Again, we just love these horizontal springs, don't we? Now it's just a block, so unlike the last one, we have something on top. As the student creates a graph of the block spring system's kinetic energy, what kind of graph is it? Always ask those questions. As shown as a function of time. The spring potential energy of the block system at 5 seconds is most nearly what? So let's highlight where we're at 5 seconds. At 5 seconds, we're right here. And I don't know if you guys are cool with this, but I'm going to say that the kinetic energy is approximately 0.25 joules right there. I'm ballparking because we're halfway between 0.2 and 0.3. Well, it's asking us about the spring potential energy at that point. I want you to think about this oscillator. When we have the most kinetic energy, how much spring potential energy do we have? None, right? So up here, it's all K, and the US is 0. And when we have no kinetic energy, what kind of energy is it? All spring, right? So if I had to draw this out, as we're whipping through the middle, it's either to the left or right, it's all kinetic. As we reach our maximum displacement or amplitude over here, we are going to have all spring energy, and it's going to keep going back and forth all the way over to here as it oscillates in simple harmonic motion. So what does that mean? That means that the total energy, the most we can have is 1, right? If it's all kinetic as 1 joule, then that means the total everywhere has to be 1 joule. And so at 5 seconds, if our kinetic energy is 0.25 joules at that point, and we know our total energy, not change in energy, but I should say our sigma energy here, our total energy is 1 joule, and that's made up of K plus US, then we just say, oh, well, kinetic is 0.25, so I guess my spring potential energy has to be 0.75 to add up to that same total. So we're using conservation of energy here as we interpret this graph. Moving right along. We have an experiment, and it looks like we're getting a graph of period squared, all right, period squared versus the length of the string. Okay, so you can read this for yourself if you want to pause the video. You don't need to listen to me read it. But it does say it's undergoing simple harmonic motion. It says the data is linearized. And it says, let's focus on the question. What information from the graph can be used to determine the acceleration due to gravity for this object? So it's saying, how can I use the graph information to get to G? Well, it's a pendulum. It said that in here somewhere. When an object is raised, it undergoes simple harmonic motion. Yeah, it's a string, and it's swinging back and forth. So we know it's a pendulum. And if we know it's a pendulum, we can go to our equation sheet and see that the period for a pendulum is 2 pi square root of L over G. So you see where we're going here, right? We're going to have to manipulate this equation so that we can get G, because it's saying, how can we use the graph to get G? So we have slope, slope, slope. We're probably going to have to use the slope. And that's why the first thing I thought when I saw this question is, what kind of graph is it? Always ask that. And does the slope mean anything? we could ask what the bounded area means, but it doesn't because it's hinting at the slope here. So the slope of the graph, that's why the first thing I wrote was t squared over L. So you see what we're going to have to do. We're going to have to take that, we're going to have to manipulate our period of the pendulum equation so that t squared over L shows up there, and then G would be in terms of that, and then there's going to be some constants floating around probably. So let's see if we can make this work. From here, I want to get t squared over L. So I want to get L out from under that radical. So I'm going to square everything. What a crazy man. All right, so here we go. We have TP squared equals 4 pi squared. And then the radical is going to be eliminated when we square it. So we're going to have just L over G. So I squared every single term on both sides of the equation. See, we're getting closer here, right? Now I'm going to divide both sides by L. So that gets me to my TP squared, period of the pendulum squared, over L. And why don't we just keep going here? Because that's going to be equal to 4 pi squared times G. And you see that if I solve for G, I'm going to write it like this. I'm going to write it like this. TP squared over L times 1 over 4 pi squared. Now, why did I write it like that? Because I know that this is the slope of the graph that they gave us. And so let's see if we can figure out what our answer is going to be. Now, I thought they were wanting me to give my answer straight up like G is this. But if you look hard enough here, you can see how this is going to tell us, oh, okay, the slope represents the quantity 4 pi squared over G. So I could rearrange that algebraically, but I think you guys see what we're getting at here. So what kind of graph is it? Does the slope mean something? Yes, it does. And we're going to manipulate the pendulum equation to get it to do what we need it to do. Oops. We just have one more for today here. It's going to be this one. A rope hangs from a tree that is on Earth's surface. Okay. Student X holds the rope and hangs from rest. Oh, so they're like chilling here at some certain point. Then student Y exerts a force, so it gets them swinging back and forth on the rope. We see a vertical position. So sorry, it's a little bit at the edge of our screen, but that would be a graph of Y. Remember, what kind of graph is it? We have that one, and we also have graph 2 shows the speed of the student as a function of the student's vertical position. Interesting. So that's a pretty funky graph we don't always see. What's the approximate length of the rope and the mass of the student if the maximum gravitational potential energy of the student Earth system is 2,000 joules? Okay. Well, if the student is hanging from a string going back and forth, maybe they're doing some jumping into a creek or something, our period for that pendulum, we know, is 2 pi square root of L over G. Now, our graph 1 here, let's take a look at this one. We notice the vertical position. So let's think about what that would look like if we had to sketch it out. We would be at the top, vertical position. We would swing all the way down, so that would get us to here. We would swing back up to the top, that would get us here. We have to turn around and come back, that would get us here. And we'd swing back to our original height, which would be here. So this graph might throw some people off because normally we're used to saying period is a full cycle, and it is. But in this case, if we think about when we arrive at those maximum heights, for a pendulum, the period is defined as all the way over and all the way back. So according to this graph, our period is actually 7 seconds. So that's going to be 7 there. And we have a 2 pi, we have a square root of L over G. It was asking us what's the approximate length of the rope. So that's one thing we're going to be solving for. And that's just an algebra problem there. So we're going to go 7 over 2 pi. We have to square that whole thing. And that's going to be equal to L over 9.8. And we'll just multiply whatever all that stuff is times our 9.8 to get the answer. Be careful with pi when you plug it into your calculator. These ones especially, they like to multiply by pi even though you're trying to divide. So just be heads up on that. And if I can make this work right here, we have L is 1.73 meters. Okay, so we got the first part. And then the second part says, what's the approximate, it says what's the length of the rope and the mass of the student. Now you might notice the period of a pendulum equation doesn't have mass. We know that the period of a pendulum does not depend on the mass at all, in fact. But it does give us enough information to figure this out. Because look, it says our UG, or gravitational potential energy, mg delta y, it does say that that maximum value is going to be 2,000 newtons. Excuse me. My 15 minutes is about to run out, so I'm going to set this up for you guys. You're going to divide both sides by that answer, and you're going to do some algebra. And if you can algebra good, the mass of the kid is 81.6 kilograms. This has been Mr. Simkins, in the Simkins Physics Corner. Make sure you hit that sub, like,